of the periodic table of elements is a set of adjacent groups. The term is first used by Charles Janet. In the periodic table, there are mainly 4 blocks. They are given below: S block, P block, D block, F block. So here we are going to discuss the D and F block elements. The D block of the periodic table contains the elements of the groups 3 to 12. The name transition metals is often used to refer the elements of D block, and inner transition metals are often used to refer the F block respectively. Transition elements involve following: iron, copper, silver, and gold. The inner transition elements involve thallium, palladium, and uranium. After reviewing this digital content, we will be able to know the electronic configurations of the transition elements, know the positions of the D and F block elements in the periodic table, describe the preparation, properties, structures, and uses of some important compounds. Learn the properties of the F block elements. Understand the general characteristics of the D and F block elements. Explain the general horizontal and group trends in D and F block elements. The D block elements are also known as transition elements. As we have discussed above, transition elements involve iron, copper, gold, and silver. The D block occupies the large middle section flanked by S block and P blocks in the periodic table. There are 4 rows of the transition elements. 3 of them are 3D, 4D, and 5D. The 4th row, 6D, is still incomplete. Electronic configurations of the D block elements. The electronic configurations of the transition elements is N-1 D1 to 10 NS1 to 2, where N-1 means the inner D orbitals which may have electrons. From 1 to 10 number, the outermost NS orbital may have only 1 or 2 electrons. The electronic configurations of zinc, cadmium, and mercury are represented by the given formula N-1 D10 NS2. Note, the half and completely filled sets of orbitals are relatively more stable. So, the electronic configurations of Cr and Cu in the 3D series is different. For example, let us consider the case of Cr, which has configuration 3D54S1 instead of 3D44S2. The energy gap between the two sets, 3D and 4S of orbitals, is small enough to prevent electron entering the 3D orbitals. The electronic configuration of some of the elements is given below. Some of the general properties of the transition elements are listed below. Physical properties: variation in atomic and ionic sizes of transition metals, ionization enthalpies, oxidation states, trends in the M2+ or M standard electrode potentials, trends in the M3+ or M2+ standard electrode potentials, trends in stability of higher oxidation states, chemical reactivity and E node values, magnetic properties, formation of colored ions, formation of complex compounds, catalytic properties, formation of interstitial compounds, alloy formation. Now, let us discuss them in detail. Physical properties. All the transition elements display typical metallic properties. They have high tensile strength, ductility, malleability. They have high thermal and electrical conductivity and show the property of metallic luster. They have one or more typical metallic structures at normal temperatures except zinc, cadmium, mercury, and manganese. They have high melting and boiling points. Variation in atomic and ionic sizes of transition metals. The ions of the same charge in a given series show progressive decrease in radius with increasing atomic number. The reason for this fact is that the new electron enters a d orbital each time the nuclear charge increases by unity. Ionization enthalpies. It is defined as the energy required to completely remove the outermost electron from an atom in its ground state. The ionization enthalpy increases along each series of the transition elements from left to right. Oxidation states. It represents the total number of electrons removed from an element or added to an element to know its present state. The elements which gives greatest number of oxidation states lies in or near the middle of the series. For example, manganese exhibits all the oxidation states from +2 to +7. Question. Calculate the oxidation state of an element N in NH3. Solution. Let the oxidation state of nitrogen be P. So, P plus 3 equal to 0. This implies P equal to -3. Hence, the oxidation state of N is -3. Note. The variability of oxidation states in transition elements arises out of formation of colored ions. When an electron is excited from a low energy d orbital to a higher energy d orbital, the energy of excitation corresponds to the frequency of light absorbed, which lies in the visible region. The frequency of the light absorbed is determined by the nature of the ligand. The colors on some of the elements of D block are shown as formation of complex compounds. The compounds in which the metal ions bind a number of anions or neutral molecules to give complex species with characteristic properties. These species are known as complex compounds. A large number of complex compounds are formed by the transition metals. For example, FeCN6 raised to power -3 and FeCN6 raised to power -4. Catalytic properties. The transition metals are known for their catalytic action. For example, iron 3 catalyzes the reaction between iodide and persulfate ions. Formation of interstitial compounds. The compounds which are formed when small atoms like H, C or N are trapped inside the crystal lattice of metals. Physical and chemical characteristics. They have high melting points. They are very hard. Some of them approaches diamond in hardness. They retain metallic conductivity. They are chemically inert. Alloy formation. Alloys are the blends of metals prepared by mixing the components. For example, the best known alloys are ferrous alloys, chromium, vanadium, tungsten, molybdenum, and manganese. Uses of alloys. Alloys are used for the production of a variety of steels. Alloys of transition metals are also of considerable industrial importance. Oxide and oxoanions of metals. Oxides are generally formed by reacting metals with oxygen at high temperatures. The highest oxidation number in the oxides coincides with the group number. The oxidation number of a metal increases with the decrease in the ionic character. It is a compound of the transition metals. The chemical formula for potassium dichromate is K2Cr2O7. Potassium dichromate is red in color. It is used in leather industry and as an oxidant for preparation of many azo compounds. Dichromates are generally prepared by treating sodium dichromate solution with potassium chloride. The structure of chromate ion CrO42- is tetrahedral and of dichromate ion is Cr2O72- consists of two tetrahedrals sharing one corner with CrOCr. Uses. Potassium dichromate is used as a primary standard in volumetric analysis. It is also used as an oxidizing agent in organic chemistry. It is a compound of the transition metals. The chemical formula for potassium permanganate is KMNO4. Potassium permanganate is violet in color. Potassium permanganate is prepared by fusion of MnO2 with an alkali metal hydroxide, and then its electrolytic oxidation leads to permanganate ions. The reaction is given as. A few important oxidizing reactions of KMNO4 are given below. First, in acid solutions, iodine is liberated from potassium iodide. Fe2 plus ions of green color are converted to Fe3 plus of yellow color. Oxalate ion or oxalic acid is oxidized at a temperature of 333 Kelvin. Nitrite is oxidized to nitrate. Second, in neutral or faintly alkaline solutions, oxidation of iodide to iodate. Thiosulfate is oxidized quantitatively to sulfate. Manganese salt is oxidized to MnO2. Uses. Potassium permanganate is used as an oxidant in preparative organic chemistry. It is used for the bleaching of wool, cotton, silk. It is also used for the decolorization of oils. The F-block elements are composed of the two series, lanthanides 14 elements and actinides 14 elements. The general symbols Ln and Ac are used to denote lanthanides and actinides respectively. The lanthanides have only one stable oxidation state. In actinides, there exists a wide range of oxidation states. The chemistry of lanthanides helps in examining the effects of small changes in size and nuclear charge along a series of similar elements. Some of the properties of lanthanides are as follows. Electronic configurations. The atoms of lanthanide series have a common electronic configuration of 6s2. The most stable oxidation state of all lanthanides is 4f to the power n, where n is from 1 to 14. Atomic and ionic sizes. A unique feature of lanthanides is the overall decrease in atomic and ionic radii from lanthanum to lutetium. The decrease in atomic radii is not quite regular. The cumulative effect of contraction of the lanthanide series is known as lanthanide contraction. Oxidation states. Sometimes the liquid solutions of lanthanide elements show +2 ions and solid compounds show +4 ions. This irregularity arises mainly from the extra stability of empty, half-filled or full-filled F subshell. General characteristics. The lanthanides are silvery white soft metals. They get tarnished rapidly in air. Their hardness increases with increase in atomic number. Their melting points range between 1000 Kelvin to 1200 Kelvin. They are good conductors of heat and electricity. The colors of these ions is attributed to the presence of F electrons. Uses. They are used in the production of alloy steels. They are also used for the production of plates and pipes. The actinides include 14 elements from TH to Lr. The actinides are radioactive elements. The earlier members of this series have relatively longer half-lives as compared to the latter ones. Some of the properties of actinides are as follows. Electronic configurations. The atoms of actinide series have a common electronic configuration of 7s2. They have a variable occupancy of 5f and 6d subshells. Ionic sizes. In this series, there is a gradual decrease in the size of atoms across the series. This pattern is also known as actinide contraction. Oxidation states. There is a wide range of oxidation states for actinide series. In general, the actinides show +3 oxidation state. The elements in the first half of the series exhibit higher oxidation states. General characteristics and comparison with lanthanides. The actinide metals have silvery appearance. The magnetic properties of the actinides are more complex than those of the lanthanides. The lanthanide contraction is more important than actinides. The actinides are highly reactive metals. Some of the applications of D and F block elements are as follows. Iron and steels are the most important construction materials. Some compounds are manufactured for special purposes such as TiO for the pigment industry and MnO2 for its use in dry battery cells. The Cu or Ni alloy are used to make silver UK coins. They can work as catalyst in the chemical industry. Ziegler catalysts used to manufacture polyethylene. Haber process uses iron catalysts for the production of ammonia. Let us summarize the main points covered in this digital content. The name transition metals is often used to refer the elements of D block, and inner transition metals are often used to refer the F block respectively. The D block elements are also known as transition elements. The electronic configuration of the transition elements is N-1, D1 to 10, NS1 to 2. All the transition elements display typical metallic properties. The ionization enthalpy increase along each series of the transition elements from left to right. Diamagnetic substances are repelled under the application of magnetic field, while the paramagnetic substances are attracted. The transition metals are known for their catalytic action. Important compounds of transition elements are potassium dichromate and potassium permanganate. The F block elements are composed of the two series lanthanides and actinides. The actinides are radioactive elements. Iron and steels are the most important construction materials. Haber process uses iron catalysts for the production of ammonia.